Welcome to the deep dive. Today we're really digging into something foundational. The big leap to 64-bit computing. It really changed everything, but maybe not in all the ways you'd expect. So our mission here is to unpack the why. What were the absolute hard limits of 32-bit? Why was 64-bit the necessary next step? And crucially, why did we kind of plateau there? And how does this all lead us towards things like RISC?
Yeah, it's fascinating because the core problem, the thing that really forced the industry's hand, it was just simple math. See, 32-bit architectures could only handle 2 unique memory addresses. Sounds like a lot, maybe, but it translates to just 4 gigabytes, a hard ceiling.
Only 4 gigs, which today sounds tiny.
Exactly. And back then, memory was getting cheaper, fast. Suddenly you had applications, think video editing, large databases, scientific simulations that needed way more memory. That 4 gigabyte wall, it wasn't just inconvenient. It was stopping progress cold, a real bottleneck.
Okay, so fixing that memory limit, that 4 GB problem, was job number one. But surely the move to 64-bit brought other advantages too. It wasn't just about RAM, was it?
Oh, absolutely not. It was a golden opportunity for an architectural reset, especially for the x86 world with x86 64, one of the biggest immediate wins performance-wise, doubling the number of general-purpose registers.
Hers, right? The processor's own super-fast scratchpad memory.
Precisely. They went from 8 to 16 in x86 64. That's a huge deal. It means the CPU can keep more of the data it's actively working on right there on the chip, less time spent fetching stuff from slower cache, or even worse, main memory. Big performance boost.
Yeah, cutting down that memory latency always helps. Okay, some more registers. What else?
Security got a massive upgrade, that enormous 64-bit address space. It makes a technique called address space layout randomization, ASLR, exponentially more effective.
ASLR, that's the thing that shuffles where programs live in memory, right?
Yeah.
Makes it harder for attackers.
Exactly. With 64 bits, there are vastly more places to hide things, making it, well, practically impossible to guess reliably. And crucially, 64-bit architectures enabled robust, hardware-enforced data execution prevention, or DEP. That helps prevent entire classes of attacks where malicious code tries to run from memory locations meant only for data.
And didn't the 64-bit switch also kind of accidentally fix a ticking clock? The year 2038 problem?
Huh. Yeah, that's a neat side effect. A lot of systems use 32-bit integers to track time, seconds since January 1st, 1970. That counter would have run out of positive numbers in 2038. Moving to 64-bit integers for timekeeping gives us, well, billions of years. Problem solved.
Okay, so memory addressed, more registers, better security, time fixed. Seems like more bits are always better. So the obvious question then is, why aren't we all using 128-bit processors now? Why did it just sort of stop at 64?
It really comes down to practicality and diminishing returns. A 64-bit address space can theoretically point to 16 exabytes of memory.
16 exabytes. That's an astronomical number.
It really is. We are nowhere near needing that amount of addressable memory for general computing. Not even close. In fact, most current CTUs don't even use all 64 bits for addressing. They typically use 48 bits for virtual addresses, which still gives each program 256 terabytes of virtual space. That's plenty.
Okay, so we don't need more address space. But would 128-bit hurt?
Oh, it absolutely would. Think about it. Every pointer, every memory address your computer uses would double in size, from 8 bytes for a 64-bit pointer to 16 bytes for a 128-bit one.
Right, so just storing the addresses themselves suddenly takes up twice the space.
Exactly. That wastes RAM, but even worse, it bloats the CPU caches. Those caches are small and incredibly important for speed, filling them with unnecessarily large pointers. That actively slows down most common tasks. You get basically zero benefit for general computing, but a definite performance hit.
That makes sense. So if 128-bit general processing is inefficient, how do we handle tasks that need to crunch really wide data, like graphics or AI?
Specialization. That's the key. Instead of making the entire architecture 128-bit or wider, we use specialized units, things called SIMD units, single instruction, multiple data. You've probably heard of extensions like AVX on Intel AMD or Neon on ARM.
Ah, right. Those have their own wide registers.
Precisely. Those units have dedicated registers that are 128-bit, 256-bit, even 512-bit wide. They're designed specifically for parallel operations on large chunks of data, like processing pixels or running machine learning models. You get the benefit of wide data processing where it's needed without polluting the core architecture and caches with huge pointers everywhere else.
So it's about targeted power, not just brute force bit width.
Exactly. And this focus on efficiency and design philosophy is where you see the rise of architectures like ARM. By 8664, while powerful, carries decades of complex instruction set computing, or CISC, baggage. It's a hybrid. ARM's 64-bit version, Arch64, was more of a clean slate, built on RISC reduced instruction set computing principles. Big focus on performance per watt.
And RISC generally means simpler instructions, more registers.
Generally, yes. While Bryce 8664 doubled GPRs from 8 to 16, Arch64 jumped from 15 to 31 general-purpose registers. It reflects that RISC philosophy: keep the core simple and fast, rely on compiler smarts, and more registers.
And that leads us to the really modern evolution, doesn't it? RISC-V.
It does. RISC-V takes that RISC idea even further because it's an open standard. It's not owned by any one company. Its real power lies in its modularity. Designers can take the base instruction set and add their own custom specialized instructions.
So like custom instructions optimized just for AI or maybe for networking tasks.
Exactly that. You can create processors perfectly tailored for a specific job, mixing standard cores with these specialized accelerators. This makes RISC-V really well positioned for the future of computing, which looks increasingly like heterogeneous systems, system on chips or SoC sense, with CPUs, GPUs, AI accelerators all working together.
Okay, so let's bring it back home for the listener. The big jump to 64-bit. Absolutely necessary, driven by that looming 4 GB memory limit. But stopping there, that was about practicality, efficiency, and avoiding the performance penalties of going wider just for the sake of it.
Right. We solved the address space problem for the foreseeable future. The focus shifted to specialized hardware for specialized tasks.
And the future isn't really about asking how many bits anymore, but what's the right tool for the job?
Precisely. And this leads to a final thought for you to consider. The battleground is shifting. It's not just by 86 versus ARM anymore. It's proprietary licensed architectures versus open standards like RISC-V. Think about what happens when anyone from a startup to a tech giant has the freedom to design and customize their own silicon without massive licensing fees. How might that freedom to innovate change the devices and technology you rely on every single day? It's a pretty fundamental shift.